Welcome students for the course on Advanced Computational Techniques. In this, we will actually discuss about nano information processing, digital signal and gates representation. We'll see how information is handled at small scales and how binary signals are used in electronic circuits through logic gates. Nano information processing. In nano information processing, multiple layers work together. It starts with the required application and system function. Then it moves to micro or nano architectures, then to circuits, and finally to the materials being used. A device represents and manipulates a computational state variable using two or more physical states. A device which represents and manipulates a computational state variable using two or more physical state. Here we represent the quantum state. The key point here is the material and the fabrication process which determine whether the required device structure can be made. Again, in nano information processing, multiple layers they work together. You can see here number of layer like architecture layer on the top, data representation is actually in the next, device layer is actually in the next is actually material layer followed by state variable. It starts with the required application or system function, then it moves to micro and nano architectures, then to circuits. A device represents and manipulates a computational state variable using two or more physical states. The key point here is that the materials and fabrication process determine whether the required device structure can be made. We'll move to the next topic of this lecture, which is digital signal and gates. The binary numbering system is a mathematical idea, but here we see how it applies to electronics. Binary is useful because it is easy to represent using physical systems. Since a bit is either 0 or 1, any medium that can switch between two states, which is actually stable, we can call two stable states, can represent digital data. This is why binary is the foundation of digital computing. Since we can actually represent those states, which is actually the foundation of the digital computing. Binary and electronic circuits. Electronic circuits fit well with the binary representation. A transistor can operate in one of the two states. Cutoff means cutoff means meaning no controlled current, or saturation, which means maximum controlled current. Cutoff meaning that no controlled current. Saturation meaning maximum controlled current. If a circuit is designed to stay in one of these two states and avoiding the middle operating region, it can represent the binary bits. If any circuit which is designed to stay in one of the states and avoiding the middle operating region, it can represent the binary bits. Transistor input at a high value. Transistor input is at a high value. The figure represents the typical transistor diagram. Let's see. In this example circuit, applying a high input voltage, which represents a binary 1. 0 we call our low voltage will be measured as a 0, will be considered as a 0 for input, and high input voltage means which is the highest value of the voltage which can actually prolong there in the circuit, will be represented as binary 1, which causes the transistor to saturate. According to the transistor diagram, high input voltage it will get saturated, which we mention here. When saturated, the output voltage becomes nearly 0. When it is actually saturated, the output voltage becomes nearly 0. So the input is a 1, but the output is 0. A voltage near the supply voltage is considered high or binary 1, and no voltage is considered low or binary 0. These voltage levels are called logic levels. Transistor input values at low input voltage. When the switch moves to other position, the input becomes a low value, which is binary 0, and the output becomes high value, which is binary 1. So this circuit gives the opposite output compared to the input value. So here we understand that whenever we give high voltage, we give high input voltage, we get the low input low output voltage, and whenever we give low input voltage, and we get high output voltage. So this we called as equivalent to NOT gate. What are logic gates? This type of transistor circuit is called a logic gate. A logic gate takes input signals and outputs a signal representing a binary 1 or 0. Gates are not used for analog signals. When several gates are connected together, they can store binary numbers or perform computations. For now, we focus on how individual gates are working. Let's discuss about inverter gate or NOT gate, which we represented now. The gate made from a single transistor is called an inverter or NOT gate. It actually outputs the opposite of the input. It outputs the opposite to the input. Gate circuits are usually shown with special symbols rather than with transistors and resistors. The inverter symbol is a triangle with a small circle indicating inversion. The inverter symbol is a triangle with a small circle indicating inversion. NOT gate schematic symbol. The triangle shape resembles an amplifier symbol. The small bubble shows inversion. Without the bubble, the symbol would be a buffer instead of an inverter. The small bubble shows inversion. Without the bubble, the symbol would be a buffer instead of an inverter. Gate symbols usually show only input and output wires. The ground reference is simplified. Like amplifiers, gate circuits require a power supply but the power connections are often not shown in the symbol to keep diagrams much simple. Not gate in circuits. If we show all power connections, the schematic becomes more detailed. But in most circuits diagrams, power lines are minimized to avoid clutter. The level VCC refers to the constant positive voltage supply. Many logic gates exist and most have more than one input. The output depends on the logical function of the gate. Let's see the truth table of the device. Okay, the truth table is used to show how a gate behaves. It lists all positive input combinations and the corresponding output. For a NOT gate, there are only two possibilities. Input 0 gives 1 and input 1 gives output 0. Truth table sizes more complex and more complex gates have larger truth tables. More complex gates have larger truth tables. A input or a two input gate has four possible input combinations. A two input gate has four possible input combinations. We can just simply understand from AND gate or OR gate. A three input gate has 8 possibilities. In general, the number of truth table rows is 2 to the power of the number of inputs. Okay, let's discuss here what are all the things we had actually seen. In summary, binary bits in circuits are represented by voltages measured with respect to ground. Zero voltage means binary 0 and supply voltage means binary 1. A logic gate inputs and outputs these voltage levels. Gate circuits are shown using simplified symbols. Gate circuits are generally shown by using simplified symbols. Power connections are usually omitted for simplicity. Truth tables show how inputs and outputs relate for each gate. That's it, students, for this session. We'll see other topic in the next classes.